Alright, are we live? We are about to go live. I think we're live. My camera is real toasty. Alright, we got one viewer. I'll wait until a couple more people get on, because apparently we are expecting a class of students to join us, though do not see them yet, so that is okay. Duplicate this scene. On the second one, we're going to turn off that. Cool. Still one. If you're watching right now, please comment in the chat if you can hear me. I think you can, but if you can't, I need to know. That would be wonderful. Thank you. Alright, we got 4 people now. Welcome, welcome. We're going to wait for a few more people to hop on, then I'll get started. Do let me know in the chat if you can hear me. I think you can, but I can't be certain about that. So, if not, oh, now we're down to 2. Alright, that's fine. Well, I will probably just go ahead and get started then. Now we're down to 1. Okay, well, welcome one person who's with me right now. I hope whoever students were supposed to watch this and or are supposed to be here right now decide to join us at a later date. This will be recorded, is being recorded, and will be available after the fact, actually immediately after the fact, which is phenomenal. That is good news, and we will get started. So, as mentioned in the title, today we're going to be talking about polarization. Polarization is an optical phenomena that is caused by the wiggling of waves. Recently I was in class and was asked to think about how waves actually are made, waves of light, I should say, how light is actually made. And I'm actually going to draw it on this for you because it's going to make more sense if I draw this, I realize. So, the question is light. Light, a wave, a particle, it is both. It is one and the same. Sometimes it behaves like one, sometimes it behaves like the other. Today we're going to be talking primarily about light as a wave that wiggles in space, in the vacuum of space. It requires no medium to propagate, and it has a specific directionality to it, which we define by what's called a k-vector. And so I'm going to do a little drawing on this beautiful polka dot board that my wife has lent me. But we will start with a coordinate system. It's always a good idea, friends, to start your drawings with a nice coordinate system so you can orient yourself in 3-dimensional space, because we live in a 4-dimensional world with 3 spatial axes and 1 time axis. So, if we start with our coordinate system, right here, which you can see in this scene right here that I'm putting in front of the camera. I guess I can actually switch cameras so you can see it better. Switch to this one. Here is our 3-dimensional space-time diagram that we are drawing right now. So you can see that. And what we're going to be looking at is we're going to be looking at a wave in space. And so this wave originates at minus infinity and goes to positive infinity. And it wiggles along an axis. and it has a certain amplitude at each point, which I will draw out here. You can see that right here on this drawing, right here, which is so beautifully done. Let me just zoom this so you can see it better and focus on it. There we go. So you can see we have our three-dimensional axes, the y-axis, the x-axis, and then, oh no, sorry, this is actually the x-axis, this is the y-axis. And I know that because if I take my hand and I stick it up in this direction and then I wrap it towards the y-axis, then my thumb should point along the z-axis. And we generally define the z-axis from left to right. This is z, x, and y, like so, z, x, and y. And this wave is propagating in space with a k vector that points in this direction. K vector. Great. So we've got a wave, it wiggles. You can think of it like a wave on a string. You can think of it like a wave in general. A water wave, perhaps, that travels. And it also has an orientation, right? And we can see that with these amplitude vectors here. These describe an orientation of the wave, which is great, right? Waves that have orientation have some basis of definition. We can also talk about not just the electric field component of the wave, which is what I've drawn here. Often how we define the wave is actually by the electric field. We can also talk about the magnetic field components as well. And so if I draw that on this diagram, it's a little bit messy in the way that I've drawn it, but you're going to get the gist of what I'm trying to show, hopefully. It would have been nice if I had built a graphic of this beforehand, but alas, I did not. So we're just going to have to do it live. So now you can see the blue line here on this plot is a magnetic field. And the magnetic field is everywhere orthogonal to the electric field. When I say orthogonal, what I mean is perpendicular. So they're at right angles to one another. This is by definition because of the way that fields are defined with the wave equations, which are vector equations that I will not go into because it's probably too advanced for this discussion. But what we are looking at here is we're looking at what's called a linearly polarized electric field and transverse electric magnetic field, electromagnetic field. And this wave is described nicely by a plane wave propagating through space at a single frequency. So it's got a single wavelength, which is defined here. This distance right here. This is what we call lambda, right? Lambda. And this also has a frequency associated with it. So the frequency is just the speed of the wave, c, which is the speed of light, over the frequency. And we can check the units on that to make sure we have it right. Right? Frequency is in hertz, and so c is in meters per second. Right? And the wavelength we can describe to be in meters. And so if we have a meter per second divided by a meter, the meters cancel, and we're left with per seconds, which is hertz. 1 per second is a hertz. Hertz. It's a little bit messy, but you get the point. 1 per second is a hertz. So, cool. We've got a wave. It's got a wavelength, and it's got an orientation of this electric field amplitude vector, right? Often we refer to that, at least in physical optics, as a hat, where a hat describes a unit vector pointing along, in this case, the x-axis, that is defining the polarization state of that light field. Cool, cool, cool. All right, we've got a polarization. We've got a wave that's traveling in space. Now, we're going to look at some waves that travel in space. First off, we're going to look at a laser. This is a laser pointer that I've got right here. And you can see that if I stick my hand in front of it, it's forming a nice spot right on my hand right there as I bring it out and forward. I wish I had some dust or powder. I have a towel that might do it. Nope, there's not enough dust on that. That's okay. I did just dust with it, but yeah, too bad, so sad. But yeah, this laser pointer that I have is a light wave. It's a coherent light wave, meaning it's all at approximately one frequency. And you can see as I track with it, I can point on a very specific tiny spot. This laser happens to be operating at the helium neon wavelength. It's a tiny little pen laser pointer, such as one that you would use in a presentation. Super fun to use, and cats love these things, so you should, if you don't have a laser yet, you should get one. But never point a laser in your eyes, kids. That is a great way to hurt yourself and actually burn holes in your retina, or worse. So don't do it. I promise you, you will regret the experience of pointing a laser in your eye. Also, don't stare straight at the sun. Let's see, there's focus. Okay, so lasers are great. They're coherent light sources. We also have what are called incoherent light sources. This right here is just an LED bar, essentially, a 2D plane of lights that are illuminating this screen. And on this screen we have taped an optical element called a linear polarizer, which is back here. We also have a linear polarizer up here. We have two linear polarizers. And right now you can actually see there's some flickering on the screen. That's because the refresh rate of my camera and the refresh rate of the LED source are aliasing. And so if we just adjust that frequency a little bit, then it takes out the aliasing and we get a much nicer view. So that is cool. But what we're going to do now is we're going to look at the effect of what's called crossed linear polarizers. And so if we have two linear polarizers that are lined up with one another, we can see the light pass through with just a little bit of reduction in amplitude. But as soon as we rotate this linear polarizer, we start to see the light go from being very bright to almost non-existent. And so what we have here is I'll draw it on our little diagram, we have the application of two linear polarizers in crossed fashion. Right here you can see what I'm referring to. So this is the first linear polarizer. Light's entering into that, and it's becoming linearly polarized along the direction orthogonal to the lines. The main reason for that is because the electric field causes electrons to shake along these linear polarizer wire. I'm not sure if these are wire grids or not. They might just be something else. But generally, a wire grid linear polarizer will cause electrons to shake along this line and will essentially cut most of the electric field in that direction, whereas the electric field that oscillates orthogonal will pass straight through. Once we hit the second linear polarizer that's taped right on the front of the screen, then we actually cut essentially the remainder of the light. And the ratio of intensities, of light intensities from before to after a linear polarizer is actually related by this law called Malus's law, which states that the intensity goes as cosine squared of the angle between the linear polarizers. So when I go from two aligned linear polarizers to two cross-linear polarizers, if I were to keep rotating this polarizer, you notice that the angle, I rotate once around and I go through two cycles of cross polarization. That makes sense because of just the orientation of the polarizers, but we also notice that the way the intensity falls off is not linear, it's actually steeper than linear. See how it stays light for longer and then it stays dark for a short amount of time. So we have this cosine squared sort of dependence. It's not linear, it's not purely cosinusoidal, it's actually cosine squared in terms of the drop off of intensity. And you can do this experiment in a lab as well. So that's the first bit here, which is great, it's fun. But we can actually take this much further and look at things like the effect of color in polarization state. So here we have another polarizer, and I'm not going to describe what this is right off the bat, but you can see as I rotate, we're actually looking at different little color tints from this LED panel. Right? You can see as I'm rotating it around, I'm seeing blue here, and then I'm seeing green as I rotate to here, greenish yellow. and then back to blue. And so essentially what we're doing is we're looking at different components of this LED, because these LED sources are comprised of a mixture of wavelengths that give them white light. We mentioned wavelength earlier, right? Wavelength is a function of the distance between peaks, right? These distance between peaks on this this plot we had here. Oh man, I just realized that my focus is probably off for all that. But if we sum up a bunch of waves that have different wavelengths, we can actually make something that's not just a coherent source like the laser that we saw earlier. This laser has a single wavelength associated with it. But if we sum, then we can actually get white light. So the summation of essentially a continuous and or an approximately continuous distribution of frequencies of light gives us a white light, which is really pretty neat. So you can see here that we can actually decompose that by using polarization to look at the different frequencies of light that are making up this white LED source. Cool. Great. Does anybody have any questions who is here right now? All four of you. If you have a question, please do send it in the chat and I will answer it momentarily. Now we're going to talk about something a little bit different that goes, it's also a color effect, but it is, I think, much prettier than, well, actually this one's not going to be color. This one's going to be related to something that you probably see every day. So here we live in the desert in Arizona, in Tucson. It gets really hot and it's really sunny a lot of the time. Though fortunately it's been cooling down lately. Thank the heavens. That's been really nice. But it's still pretty sunny out right now. And so when I went outside to work in the yard this morning, I put on a pair of polarized sunglasses to cut some of the glare from the sun that was shining into my eyes. So we ask then maybe, how do polarized sunglasses work? Well, polarized sunglasses work on the principle of linear polarization. And so these are not very good polarizers, but they work well enough. And so you can see if I rotate these sunglasses, these aviators, 90 degrees relative to the polarizer in the back and the front. These are both aligned right now, so I'm essentially using just one of the polarization angles. You can see as I rotate them to the side, we block out the polarization and we get almost no light through. Whereas if I rotate them this way, I get a tint, but light passes through. You can see if I go the other way, same thing. And so what I'm doing is I'm actually looking at the cross-polarization state of the sunglasses. And using this, I can actually determine what is the polarization state of both the sunglasses and the LED screen / rotator analyzer polarizer setup. And the reason I can do that is because I know something about polarized sunglasses. And what I know about them is that when you put them on, they are designed to block light that is S-polarized. And when I say S-polarized, imagine I flip the effect, or flip the definitions that I described here, where this is E and this was the M, or the magnetic field. This is the electric field, and this is the magnetic field. And now instead, if I have the blue line as the electric field, then what you're looking at is essentially S-polarized light if I take this plane underneath it to be the ground. And if I take this light and rotate it like so, and then I bounce it off of a plane, say like a surface of water, and or the atmosphere of the Earth, what's going to happen is that light is going to skip, hence well, it's not actually why it's called S, but that's the mnemonic for remembering which is S and which is P polarization, but that light is going to skip. That's got that orientation. It'll skip off the surface and then come straight up. And this is why when you're looking at the water, say if you're out on the Gulf of Mexico or Gulf of California, or just on the ocean in general, or a lake, if you look down at the water and it's a sunny day and the sun is close to the horizon, you can see a really bright glinting glare. But if you put on a pair of polarized sunglasses, then you actually cut that glare almost to nothing. And the reason for this is because these polarized sunglasses actually they eliminate or nearly eliminate the S-polarized light. No polarizer is actually perfect. There's a function called the polarization extinction ratio, PER, which describes how good of a polarizer you have. So no real polarizer is truly perfect, but alas, we can have pretty darn good polarizers. So now we're going to look at something called stress birefringence. I still don't see any comments in the chat. That's okay. You don't have to have questions. So here you can see I actually have a pair of my glasses that was wearing until a moment ago, that we're going to focus on if I can see them. I need to put them back on to focus again. I should not have adjusted the focus knob. My apologies. Oh, that was actually pretty close. Cool. Okay, so this is my glasses. These are my glasses. They're very cheap. They're very poor quality glasses, and they have a very interesting characteristic to them, and that is that they experience something called stress birefringence. So these are really cheap. They cost me like 37 bucks, which means that they were not made very well. And when the glass was made that was put into these sunglasses, it underwent a lot of stress when it was being annealed. You can think of stress just like you feel stress when you're stressed about school. It's the same thing. Glass can undergo stress when it's being cooled if it builds up pressure in different points during the cooling process. And so that stress birefringence that builds up, basically what that birefringence is it just is a difference in the polarization or the refractive index with respect to polarization. And so you can see as I rotate this polarizer, I'm actually analyzing the stress birefringence of the optical component that is my glasses. You can also see that one of these was made much better than the other one. They're both pretty bad, but the left lens is certainly worse than the right lens. So this is the effect of stress birefringence on optics. This is a characteristic that we do not actually want to see in optics. We can use it for certain things, but generally speaking, if you have stress birefringence in an optic, it is not a good time. It means that different polarizations are going to refract differently. And the amount of stress birefringence in my lenses, especially since they're not actually giving me any true optical power, they're just shifting the focus position onto my retina because I'm nearsighted or myopic. They're not super noticeable for me personally. But if you use an analyzer like what we just did there, you can actually see very clearly what the effect is. We also have polarizers that we can put on our optical elements. You can see right here, this front filter that I have on this lens is a circular polarizing filter. And if I rotate this thing, I can actually adjust the polarization state coming through the back of the optic. And so we might actually be able to see if I zoom way in and focus right through here. Let's bring that like so. And I rotate this guy, you can see right there, by rotating the front, I'm rotating the front of this filter ring here, I can actually cut a certain polarization. And I call it a circular polarizer because this optic on the front here is actually a circular polarizing element, which we've only mentioned linear polarization so far, but it turns out you can actually have light that rotates around the optical axis in its polarization state as it propagates through space. So it's doing a little curlicue, doing like a corkscrew where it's going like this as it's propagating through space, rather than just this up and down, or side to side, or just all over the place if it's unpolarized, such as maybe sunlight that hasn't scattered or reflected with any sort of polarization. And yeah, you can imagine that this circular polarization or elliptical polarization, even if you have light that's not just going in a circle, but is also actually elongated along one axis, that can result in some very interesting things. And so we use this in photography to cut polarization states, because we don't actually want to cut all of the light like we do maybe with an analyzer like this, where we want to cut out all the light. What we want to do is we just want to selectively say we only want, like, say, the P polarization. We don't want S polarization, which can be really nice if you're using this lens here and you have a glare on the side of your face when you're on your Zoom call. You can just rotate that circular polarizer on the front of the lens and it goes away just like that. Cool. Okay, so I think I have one more, maybe one or two more things for you. here we actually have a polarized graphic here. And I'm going to need to increase the exposure to get this to be visible. That we can do. Great. Okay, now it's visible. Let's make sure the focus is right on. I'm actually going to put it, we'll put it right up against here. Now we're getting a lot of reflection on there. So I'm just going to tip it down and see if I can cut the reflections. No, that's fine. Okay, you can kind of see it's there. It is currently visible, and it is in the field of view of the camera. So we have this graphic, right? And as we go ahead and we rotate the polarization state, we can see the graphic change pretty substantially. And so this is a polarization inversion, where the darks become light and the lights become dark. So here we can see that we've got like a light background with dark filled in. And then if we rotate, we can see the other part of the image where it's just dark background, light filled in. You almost can't even see the fisherman anymore. You just see a fish jumping, which is particularly fond for me because I do love fishing. I went fishing this weekend and I only caught one fish, but it was a blast. So yes, we can do cool things with art as well. We'll look really quickly at this optical element. This optic was made by Optimax. It was made by Optimax, and it's a very simple singlet lens. And what I'm going to do with it, I'm actually going to use it as a mirror surface. And so if I point it at just the right angle, you can see the reflection of the sunlight out here. Sunlight. And if I rotate this guy, you can see I go from seeing a whole bunch of sunlight like that to seeing almost no sunlight. And so this again is essentially the same thing that I mentioned with the skipping polarization, S polarization, which is why sunglasses are designed, polarized sunglasses are designed to block S polarization. So that is the dealio with this wonderful optical component, courtesy of Optimax. I think that's, a couple more things for looking at stress birefringence, just because I think it's fun to look at these. Here is a cup, a plastic cup. Plastics can also exhibit stress birefringence. I mentioned glass earlier, but we can see that plastic also has a very beautiful stress birefringence pattern, and it's very useful to look at these stress birefringence patterns with white light, because you can actually get a really exotic sort of dispersion pattern because of the different refractivities for different wavelengths, which is pretty cool. So you can also see a little bit about the manufacturing process, how this plastic was slumped or molded, and you can see things like different surface features. This plastic does have kind of like a wave-like pattern on the front of it, but we can also see how that wave-like pattern has stress built up in it from when it was manufactured. Spoons, much the same. Spoons also have a beautiful stress birefringence pattern. I think the spoon looks particularly neat just because it has this like binodal shape to it. And a lot of my work right now is focused on binodal astigmatism, which is a complicated nodal theory aberration concept, but can also be applied to analyzing stress birefringence patterns. So that's pretty neat. And then finally we have a protractor. This is a compass, not a protractor. For measuring angles, also a plastic component, and has substantial stress birefringence from its manufacturing. Pretty cool. Yep. Especially looks cool on a black background, I think. And we can double these up and look closer. Great. I think that is all I had to share. Does the dollar bill have any polarization security features? You know what? I have heard that it does. I do not have a dollar bill on me right now, but I can go get one. Maybe I do have one. Yeah, I read that somewhere. I've never actually tested that. Not some good question. I would also like to know if there are any Any polarization security features associated with a dollar bill? I don't think I have one in the room. Let's see if we have something in this case that would... Nope, that's not a dollar bill. Here, let me just go get one. I will be right back. I have one right around the corner, and that's if I don't kick my camera over. Came in clutch, and she brought me some dollar bills. These all look old, so I guess we'll see if they have anything going on, but we're going to zoom back in. I'm going to fix my camera real quick. I think what I've read about this is that it's actually more like a $20 bill, or one of the new fives, I think, might have one of these features. But that's not to say that these $1 bills will not have anything. But we're going to take a look and see. I'm going to raise the ISO a little bit so we can get a nice, good look. Just pocket these dollar bills for later. Thank you, Addie. And do checks. I believe there are some banks that have checks that do have polarization features. I know a lot of them are more transmission based, but that's not to say that the transmission polarization contributions would be essentially what they're checking for. So I do know that there are especially banks that have more modern checking systems with modern security features. They have, let's see, I need to fix the focus a little bit. Right there. They definitely have checks that have some sort of security feature that is built into the transmissive properties of the check. Addie says, "Hey, yes, I'll give your dollar bills back, Addie. They're based there. We share our dollar bills, so you will be getting these back." Yeah, I don't know. I don't see anything on this dollar. That's okay. Hey, Addie, since you're in the chat right now, do you want to go grab a $20 bill from my wallet that I think I have in there? Please. Thank you. But yeah, good question. I actually have another optic right here that I'm kind of curious about looking at with this polarization analysis. This is a chunk from the center of a Cassegrain primary mirror that I made. Doesn't really look like there's anything much going on with the polarization. Yeah, I mean, this is just a chunk of Pyrex that's got a polished front surface and a rough back surface. But we can still use it to see the effect of cutting S-polarized light. Just cuts it beautifully there. It's great. I have some other optics in the room that are kind of fun to look through as well. This one might actually have, oh yeah, this one. Let's see if this one has a coating on it. It does have a coating on it. Thanks. Addie brought me the 20. We're going to look at the 20. And let's see. Is that in focus? That is. Oh, you know what? There might be something on there. I'm having a hard time seeing if there is. Let's put it right in the focal plane. Yeah, I don't know. There's definitely like some kind of shadow looking thing. Is that Jackson? Who is this? I think this is Andrew Jackson. Yeah, Jackson. Andrew Jackson. What a guy. Very progressive president, if there ever was one. He did a lot for a lot of people. Yeah, I don't know. It's pretty to look at, though. Cool. Yeah. I don't know. I guess maybe it's just on the new fives where they have these features, but I couldn't tell you because it does not seem that I can determine it from this. Let's see, this one is not coated. This one, oh, this is definitely coated. This has a mag fluoride coating on it, so should be able to see some interesting. Oh yeah, there you go. So you'll notice here in this is a nifty 50 millimeter lens, and it has a magnesium fluoride coating on the front. If I rotate this analyzer, you can actually see different components of the reflection coming off of that mag fluoride coating. That would be easier if I kept it in focus. And so these coatings are actually used on the front and internally within optics to cut down on what are called Fresnel reflections. Fresnel reflections are, they are, oh, there's more, yes, I will try turning around. Sorry, I didn't have the chat scrolling, so I will bring that dollar bill back up in a sec. But yeah, these Fresnel reflections are polarization based, and so you can actually see the different polarizations bouncing off this mag fluoride coating at different angles and with different polarization components. But yes, let's look at the back of the 20. Let's see, is that in focus? It's pretty close to focus. Here, I'm going to raise the ISO again. Right. Okay, I need to turn this fan off. It's blowing this dollar bill all over the place. Alright. Let's see. Huh. I feel like those, I should just look at it right here too. I don't know. So there's definitely kind of like a border looking thing on the bottom. It's really hard to see with the lens I have on right now. Here, let's move it closer so you can get a better look at it. I'm going to bring the focus all the way in. See if I can put it right there. So I'm looking down at the very bottom of the dollar bill. Oh, that could just be the border on the other side that I'm seeing that's illuminated from the back. Let's see. I feel like there is supposed to be something really evident here, but I don't remember where it is. Natsun, can you, if you know where it is, you can definitely tell me where it is and where to look. Because like I see the shadow figure on there, but I think that's just like a transmission thing that you can see if you hold it up to light. I think it's the newer dollar bills that have the features on them. So cool to look at. It definitely looks different when it's illuminated from the back. All right, well, if there are no more questions, I have to go to class in 5 minutes because I am still a student. So I'm going to go do that. And yeah, if you have any more questions, feel free to send them in the chat. And I will check back periodically throughout the day and see if I can answer more of your questions. Yeah, thanks for joining me today. Appreciate it. And have a good rest of your day. Bye, y'all.